Okay, welcome to the Unit 7 Lesson 4 on logarithms as inverses. Today's video, we have some learning targets of changing forms between exponential and logarithmic expressions or equations and evaluating logarithms. And then we're going to find the inverse of a logarithm function. All right, so before we get started with those, let's kind of go into a little bit about the characteristics and properties of a logarithm. All right. So the first thing here is that a logarithm is the inverse of an exponential function. All right. So remember, that's going to be a big part of what we do here, and understanding that inverses, right, switch x and y's. Right. An inverse function, the basic definition is that the x and y values switch places. So a logarithmic function is also going to be one-to-one, which just means that for every x value there is one y value, for every y value there is one x value, right? They have a one-to-one correspondence, which means a log function's inverse will be a function as well. Logarithmic bases are going to be restricted similar to the exponential bases, right? So if we can remember what those restrictions are, I know that b has to be greater than 0, all right? I can't have a base b of 0 in exponentials. I can't have a base b of 0 in a log. It can't be a negative base, right? It can't have -1 or -2 or -3, so it has to be greater than 0. And then there's one more restriction, is that the base cannot be equal to 1. All right? So those are our restricted bases for logarithms, which are the same as the restricted bases for exponentials. All right? Our special bases are going to be the common log, which you'll see written as something like log of x, right? And you notice there's no base written here. Well, that's going to be understood as log base 10 of x, where the base is a 10. So when the base is a 10, we're not going to write it in. We're just going to leave it log base x. All right? And we call that the common log. When you see the word natural log, that looks something like ln of x, right? Where again, there's no base written, but if it's ln, you should understand that to be the same thing as log base e of x, right? And the base is going to equal e. So if it's ln with nothing, the base is e. If it's log with nothing, the base is 10. Any other base is going to be written in this spot in the expression. All right? The last property that we're going to talk about here is that you cannot take the log of a negative number. So in this case here, x will always be a positive value. Now, if that's been shifted left or right, of course, you can then get into some negatives. But in the end, you can't have something that looks like this. Say log of -3, right? If this value, if you're taking the log of -3 in the end, that is going to be no real solution. All right, so can't do that. All right, so those are kind of our properties and the things that you're going to keep in mind as we go through changing forms and evaluating and eventually finding the inverses. Okay, so we're going to talk now about how to change forms. All right, whether you're given an exponential or a logarithmic function, you're going to sometimes need to be able to change its form. Right, so what's important here is to understand is we're not doing an inverse yet. What we're doing is rewriting it so that it looks like an exponential form or it looks like a logarithm. But when we're changing forms, we're just rewriting it to look different. All right, so as you see here, if I'm given a function y equals b to the x power. All right. What I can do here is change this, right, so that it's in log form by taking the log of both sides. So if I say log base b of y equals log base b of b to the x, right? So what have I done here? I've added this to this side, and I've added this to this side. I've taken the log of both sides. And what that's going to end up doing is I'm left with log base b of y is equal to, now this is a property here. Anytime you have a log base b of b to the x power, that's just going to cancel out, and you're just going to be left with the exponent x, right? So, for instance, log base 5 of 5 squared is 2. Log base 6 of 6 to the 10th power is 10. Log base 3 of 3 to the x power is x, right? So anytime the base, you're taking the log of a number that is the same as its base, it just becomes, they just cancel out. It just undo each other, and you're left with just the exponent. All right, so that's a powerful property that you have to be able to understand. And what happens here is, if you notice, right, I had a base b with an exponent of x equal to a y. Now the y is in the x position and the x is in the y position. Now these are not inverses of each other. It's just rewriting into log form. These two things are actually equal to each other. This expression here is the same as this expression, right? They're equal to each other. They're equivalent. They're just written in different forms. So if I'm converting to log form and I have 5 to the second power equals 25, the long way would say log base 5 of 5 squared equals log base 5 of 25. Cancels out, and I'm left with log base 5 of 25 equal to 2. Now, understanding that whole process, we can kind of just take a shorthand version of this and say, okay, my base is 25, so I'm going to write log base 25, and then I'm just going to switch these two positions. So log base 25 of 5 is equal to 1/2. And that's it. All right. My base always remains the same, right? The base always remains the same. And then these two numbers switch positions. Again, this is just writing in equivalent form. This is not an inverse yet. So if I'm going to rewrite this, it would be log base 5 of 1/5 is equal to -1. Now remember, this one, some of you might say, hey, you can't have negatives. It's okay in this scenario. Remember, you can't have a negative base, and you can't take the log of a negative number. But the answer, right, to a log question, the other side of the equal sign for a log is okay to be negative, because essentially that's an exponent, and we can have negative exponents. So try this one, see if you can rewrite that one. Pause the video, give it a try. All right, so you should have ln of 1 equals 0. All right, let's get my pen back. And that should be what you have. All right, so let's go in the other direction, right? Let's convert from log form into exponential form. So again, identify your base. My base is 4. and I'm going to raise it now. These are going to switch positions. So 4 squared equals 16. That is now exponential form. 16 to the 1/2 power equals 4. Again, identifying the base and then raising it, turning the equals into the exponent. So 4 to the -1 equals 1/4. All right. So again, this should seem pretty redundant a little bit. Let's go ahead and see if you can do these next two. All right. Pause the video and try these next two. Okay. Hopefully this wasn't too tricky. Hopefully you recognize since there's no base here, it's a base 10. And since there's no base here, it's a base E. All right. So that's our converting from log form to exponential, from exponential to log form. Now let's get into evaluating. All right. When we ask you to evaluate, there's no equal sign, right? I'm just asking you to figure out what it's equal to. So in this case, you are going to be allowed to say, okay, well, this is equal to some number x. So since I understand that this is equal to some number x, I can reevaluate it and say 3 to the x equals 9. Now you should be tying back to the day 3 notes and say, okay, well, 3 to the x equals 9, so 3 to the x equals 3 squared, so x equals 2. So log base 3 of 9 is equal to 2. The solution is 2, right? Anytime you see a log base 3 of 9, you can substitute in a 2. Log base 10 of 1, well, anytime that you're taking a log of 1, the solution is 0, right? Because what's the exponent that you raise any number up to get 1? And it's 0, right? You could say 10 to the what equals 1? 10 to the 0. 0 is your exponent. All right, so again, let's try this one. 4 to the what is equal to 1/4. So let's flip this. Let's say 4 to the x equals 4 to the -1, right? Because fractions are reciprocals, which mean they're negative exponents. So this is equal to -1, right? And so that's kind of what we're trying to figure out here, is we're evaluating by using an exponential form to evaluate. All right? So why don't we try this next one? So again, e to the what equals e? Well, 1. Log base e of e is 1. So log base 3 of 3, this is 2 times log base 3 of 3. Remember, the base and the log are the same. It's 1. So 2 times 1 is 2. This is 3 times ln base e of 2. So this is 2 times 3, which is 6. So again, right, if you want to do this the long way, you could say 3 to the what equals 3. Well, okay, so that's 1, and that's how this becomes 1. And then it's 2 times 1, right? This one, we're saying e to the what equals e squared. Oh, well, 2. So that's where that 2 comes from. And then you're multiplying by 3. So 3 times 2 is 6. Okay? So now we get to the heart of what we're trying to get you to be able to do, which is to find the inverses of each log. So the first thing we're going to do here is isolate the logarithmic expression. All right, so first thing we have to do is have something equal to the log of something. right? Then we're going to convert to exponential form. Then we're going to switch the x and y variables and finally solve for y. All right, so isolate the log, convert to exponential form, switch the x and the y, solve for y. So what does that look like? Well, the nice thing here is that this one's already been isolated. You see there's nothing happening to the log itself. Log base 8 of this expression x plus 2. So I can just convert that easily and say 8 to the y equals x plus 2. All right, so all I did was rewrite this in exponential form. I switched my y in this. Now I'm going to switch x and y. So 8 to the x equals y plus 2. And that's the inverse part. Once I switch x and y, I've now created an inverse. Now I need to isolate my y by subtracting 2. So it's 8 to the x minus 2 equals y. And I could write that in function notation. The inverse is equal to 8 to the x minus 2. Now, this negative 2 is not happening in the exponent. It is a whole number being subtracted from this quantity. So you could kind of think of it that way. Okay? And that's important, and you'll see in some of the next examples why that's important. But if we think about what's happening here, right? If in this log function, this translation is left 2, right? It's going backwards 2 in a negative direction. But when we switch x and y's, the horizontal movement will become our vertical movement. And this is telling me that this exponential will go down 2. So left 2 now becomes down 2. And you should understand that those are reciprocal moves. Okay? So let's look at our second example here. And in this case, our log is not isolated. Here's my log expression. Since it's not isolated because I have this plus 3 here. So what I'm going to need to do is move that over. Y minus 3. And I'll put that in parentheses to kind of show you that it's one quantity now. It's one thing that's going to be moving. And that's equal to log base 7 of x minus 1. Now I can want to convert. So I have 7 raised to the y minus 3 equal to x minus 1. Okay, so again, all I did was take this y minus 1 and put it with the 7. And this x minus 1 is now by itself. So that is rewriting in exponential form. All I've done is rewrite. Now, when I switch x and y, now the x and y have switched positions. Now that I've done that, now it's an inverse. Now I've taken the inverse. And now I need to solve for y. So I'm going to get y equals 7 times x minus 3 plus 1. And then if I'm going to rewrite it in inverse notation, I'll say f of x equals, or f to the negative 1, the inverse of f of x is 7 x minus 3 plus 1. Write that a little neater. All right, and that is my inverse, right? And again, we can talk about these translations. What's happening here? Well, this was right 1, up 3. Right 1 is a positive move, and its corresponding positive move is up 1. up 3 is a positive vertical move, so its inverse would be right 3. So you see how the vertical became the horizontal became the vertical, right? That's the essence of an inverse, all right? So let's take one more look, one more example here, and we'll be done, all right? Again, we want to isolate, right? So this is really the trickiest of all the problems we've done here, and that's understanding how we're going to isolate, right? If I was solving an expression, right? If I had y equals negative x plus 5, the first thing you would do is subtract 5. So y minus 5 equals negative x. Then you can convert that to x equals negative y plus 5. Okay? That's what we're doing here. This process is isolating the x. What I want to be able to do is to isolate this expression. So I'm going to follow the same process. Minus 5 on both sides. So negative log base 3 of x minus 1 equals y minus 5. Now I'm going to convert everything. So log base 3 of x minus 1 is equal to negative y plus 5. And then what am I going to do? Now I'll rewrite it. So 3 to the negative y plus 5 is equal to x minus 1. Now I can take the inverse by switching my x and my y. And then add 1, so I end up with the inverse is equal to 3 negative x plus 5 plus 1. And that is how to find an inverse of a log function. All right, we'll practice a lot of this. Once you start doing the practice, it's not going to be so bad. Just remember those steps. Isolate, rewrite, find the inverse, solve for y. And those are the steps you need to take. So we'll practice this in class. And if you have any questions, let us know.